In this video, we will discuss about the internal direct product. So our topic is internal direct product. Okay, in short, we write down as IDP, IDP. So we define this IDP as let G be any group and H and K be any two subgroup of G, be any two subgroup of G. So then G is called internal direct product. Internal direct product of H and K if and only if first point each element of H commutes with each element of K with each element of K. Second point, each element of G each element of group G can be expressed as the product of one element of H by one element of K, one element of K uniquely. So these two properties. So when these two properties follow by a group G with the H and K be to subgroup of G, then G is said to be a internal direct product. Now we will take the theorem for proving this. So now we have the theorem based on this. Let G be any group, G be any group is an, or we can say that be the internal direct product, group be the internal direct product. In short, we write down as IDP of H and K. H and K both are subgroups of G. So then prove that first part is H intersection K. So H intersection K is equal to identity element. So that means only one element is common, that is the identity between H and K. So second part, G G is isomorphic to external direct product. G is isomorphic to external direct product, external direct product of H and K, H by K, we can write down as H by K. So that is, you can write down as G is isomorphic to H by K. So now we shall prove this. So first, when we are going to prove the first part H intersection K is equal to E, that means the identity element is common between them. So now we take as, so for proving the first part, so let we assume that X be the element which belongs to H intersection K. So H be the element which belongs to H intersection K. So this implies that X belongs to H and X belongs to K. So X belongs to H and X belongs to K. So now we write down as G. G be the IDP, internal direct product of H and K. So that means we can say that for every small g be the element of G. So can be expressed as G is equal to HK. Okay, we have the first property. Each element of H commute with each element of K, or each element, second property, each element of G can be expressed as the product of one element of H by one element of K. So we can take as H belongs to H and K belongs to K. So and the representation, so we also remember this, and the representation is unique. So representation should be unique, but we can take as so here we can write down H belongs to H and K belongs to K. So now we can write this as, we can write G. G is equal to HK. So you can do this small k. So G is equal to HK. So this can be written as, this equal to H X into X inverse into K. So X into X inverse, this is equal to identity. So you can write down this as, uh, you can write down H into E into K. So this can be written as X into X inverse into K. So identity E can be written as in this form. So now we can write down this as first as Hx, and second we can write down that X inverse into H. So this we consider as equation number 1. So now we have a X. X belongs to H. So X belongs to H. So X be the element we have already considered which belongs to H and K. That means H intersection K. So X belongs to H or X belongs to also K. So when K be a subgroup means it is inverse also exists. So that means X inverse also exists. So X belongs to H and H belongs to H. So X belongs to H or H belongs to H. So this can be written as XH is also belongs to H. Similarly, when X inverse belongs to K, X inverse belongs to K and K belongs to K, so which implies that X inverse into K is also belongs to K. So, but by uniqueness of representation, so by uniqueness of representation, that means we can write down as H is equal to HX. So this can be written as HE is equal to HX. This can be written as HE is equal to HX. So now by using the left cancellation law, so by using left cancellation law, so by using left cancellation law, this can be represented as E is equal to X. So we can say that X is equal to E. So X equal to E. So when X is equal to E, it means that when we are taking the element x which belongs to H intersection K, so that means the identity element. So hence we can write down as hence H intersection K is equal to E. So it means that E is only the element. E is only the element common to both H and K. Common to both H and K. So this is our first part. So this is our first part. Now we shall move to the second part. So for proving the second part, so we write down a let G, small g, which belongs to G. So then G is equal to HK is product for some uniqueness. So for some unique, so which we can write down as H belongs to H and K belongs to K. So to prove that G is isomorphic to H by K. G is isomorphic to H by K. So this is the second part. So now first we define the function for proving this. So we define the function phi. Phi we defined from group G to H by K. So G to H by K for proving the isomorphic to H by K. So we can write down by setting. So what is the function? Function we can define as phi of HK. Phi of HK is equal to H comma K. So this is our equation number 2. So this is our equation number 2. So because this is the Cartesian product. Or Cartesian product element can be written in the form of order pair. Order pair. So that can be written in the form of H and K. So order pair. We follow the order pair. So now first we will prove that function is homomorphism. So for proving isomorphism, so first we shall prove that function is homomorphism, then function is onto, one onto. So first we prove that function is homomorphism. So for proving homomorphism, so we take as, so let here we write down the function basically. Okay, so this can be considered as for g, small g, g equal to hk. Sorry. So this we can write down as, so let G1. G1 is equal to H1 K1. We take two elements, and G2 is equal to H2 K2. So both are belongs to G. So both belongs to G. So then we write down the function phi of G1 into G2. Phi G1 into G2, that can be represented as phi of G1 G2. What is the value of G1 G2? G1 G2 value is H1 K1. So H1 K1, H1 K1 into H2 K2. So H1 K1 into H2 K2, this will equal to, basically you write down the product of H and K. So there is no issue for that. So you can write down, so this can be written as phi of H1 K1 and H2 K2. So this can be written as H H. So means first element. So first element that can be written as uh, phi of H1 H2. So this can be written as phi of H1 H2 and K1 K2. So we can write down in this form. So each element of S, so we can say that each element, each element of H commutes with each element of K. So with each element of K. So we can say that uh, K1 into H2 can be written as H2 into K1. So you can write down this as, so now, so this is equal to, this equal to, so first we write down in order pair. So H1, H2, first element we taken as H1, H2, comma, K1, K2. So this we can write down as, so H1, H2 into K1, K2. So this can be written as in the order pair H1 into K1, H1 into K1, and second bracket order pair we can write down H2 into K2, H2 into K2. So this equal to, so this can be written as by definition function of H1 K1 means H1 K1, or this can be written function of H2 K2. So function of H1 K1 or H2 K2. So this will be equal to function of G1, and this will be equal to function of G2. So we have taken the function of G1 G2, which is equal to function of G1 into function of G2. So we have considered as G1 into G2. So we can say that phi, function phi is homomorphism. Phi is homomorphism. Now, second part we shall prove that phi is onto. Sorry, 1 1. So second part we shall prove that phi is 1 1. So function phi is 1 1. So for proving function phi of G1 is equal to function phi of G2. We take two element of G, then we shall prove that G1 equal to G2. So for proving 1 1 function. So now you can write down this as phi of H1 K1 is equal to phi of H2 K2. So we take two element H1 K1. So this we can write down as H1 comma K1 is equal to H2 comma K2. We write down in order pair. So here we can say that when the two order pairs are equal, it means that H1 is equal to H2 and K1 is equal to K2. So K1 equal to K2. So now G1, when we write down G1, so what is the value of G1? G1 will be equal to H1 K1. So H1 K1, so that means these two are equal. So this can be written as, so H1 equal to H2 or K1 equal to K2. The H1 K1 can be written as H2 into K2. So H2 into K2, or this will equal to G2. This will equal to G2. So it means we can say that, which implies that G1 is equal to G2. So when G1 equal to G2, it means this say that function is 1 1. So function is 1 1. So after proving function is 1 1, we shall prove that function is onto. If function is onto, then we can say the function is isomorphism. So that means third part, we shall prove that phi is onto. So phi is onto. So let we can take the element of set B means h by k. So let hk be the element of h by k. So here we can say that h belongs to h, and k belongs to k. So then a element hx which belongs to G, such that we can write down as phi of hk. Basically, this is not x, this is k. So this is phi h of k. So phi of hk is equal to hk. So we can say that function is onto. So hence phi is onto. Is it having the pre-image? Function is onto. So this can be written as G is isomorphic isomorphic to external direct product h by k. External direct product h by k. So G is isomorphic to h by k. So we have proved. this theorem.